Hello. Well, in this video, we'll be looking at cubes, cube roots, and how they relate to the binomial theorem, and also a special method for doing binomial expansions using calculus. So I'm actually going to start with cube roots, and we'll be looking at cubes of two-digit numbers and the cube roots of two-digit numbers which have been cubed. So I'm just going to set out here by way of introduction 4 examples of cubes, namely 20 cubed, which is 8,000, 21 cubed, which is 9,261, 29 cubed, which is 24,389, and 30 cubed, which is 27,000. And the reason for this is that I want to point out something about the cubes. If we just look, partition the numbers and just look at, we partition them there so that there are 3 digits after the partition. Now if we look at the numbers before, you will see they range from 8 up to 27. So on all the cubes of numbers between 20 and 30, the minimum value will be 8,000, the maximum value will be 27,000. And that means that we can investigate these numbers to find out the initial digit of the cube root. And also we're going to look at the final digit of the number being cubed and the final digit of the cube itself. So here we've got a 1 and a 1 and a 9 and a 9. Now over here I've set out the cubes of the first 9 digits, and you'll need to commit these to memory, but there is a pattern in the last digits of the cubes. So where a number ends in 1, its cube will end in 1. If a number ends in 2, its cube will end in 8, and 3, the cube will end in 7, 4 and 4, 5 goes with 5, 6 goes with 6. If a number ends in 7, its cube ends in 3, and a number ending in 8, its cube ends in 2, and 9 goes with 9. And you'll see here the pattern that we have here the 2 and the 8, 3 and the 7, and the 7 and the 3 and the 8 and the 2. So these are complements from 10 of each other. These are number partners, 2 and 8, 3 and 7. And for the rest, the final digit of the cube is the same as the final digit of the cube root. So then that's all we need to know. So I'm going to move into the first example is find the cube root of 148,877. And we first partition the number counting 3 digits from the right. So we partition it here. The last digit here is a 7, and that corresponds to a 3. So the cube root ends in 3. And here on the left we've got 148. Well, the largest cube that is less than 148 is 125, which is 5 cubed. And so the cube root of 148,877 is 53. And next example, 438,976. Again, we partition the number here. Look at the final digit, it's a 6, and so the cube root ends in 6. 438 on the left is less than 512 but more than 343, so the number here is 7. The cube root of this number is 76. Another example, 753 571. Partition, the last digit is 1, and so the cube root ends in 1, and 753 gives us a 9 here, because 729 is the largest cube less than 753. And not always are there 3 digits on the left, so with this example 13824, we partition here, counting 3 digits from the right. The largest cube less than 13 is 8, so that's a 2. And a 4 is the last digit, and so the cube root is 24. And the Vedic Math Sutra for this process is by the last digits, by the last digits. So I'm going to put up 3 here for you to practice. 54872, 300, 763, and 132, 651. And you can stop the video for a minute and have a go at those, and then I'll put up the answers for you. So the answers here are 38. It's 38 cubed is this, and this is 67 cubed, and here we have 51 cubed. Okay, now we're going to look at a very neat method for cubing 2-digit numbers. And we'll start with a simple example of 12 cubed. The method is to use a proportion. The sutra involved is proportionately. The first step is to set down the cube of the first digit. So 1 cubed is 1. And then we use set out 3 more terms of a geometric progression using the ratio of these 2 digits, 1 to 2. So the proportion is doubling. So 1 doubled gives 2, 2 doubled gives 4, and 4 doubled gives 8. So there we have a geometric sequence. The next step is to double the middle 2 digits, 4 and 8. And then all we do is add up the digits. Here we've got 8, here we get 12, and 7 and 1. So that first step was to set down the cube of the first digit, and using the proportion, it turns out, as will become obvious later on, the last digit here will be the cube of the second digit of the number we're cubing. So this 8 is 2 cubed. Let's look at the next example, which is 13 cubed. Set down the cube of the first digit. The proportion this time is 1 to 3. So we triple 1 to give 3, triple the 3 to give 9, and triple this to give 27. We double the middle 2 numbers, and then sum up for the answer. Here we have 7 with 2 to carry, 29, it's 9 with 2 to carry, 11, and 2, 2197. Let's look at 21 cubed. We set down the cube of the first digit, so that's 8. And this time the proportion is going down, the ratio is 2 to 1. So we divide by 2, divide by 2, and divide by 2. And double the middle two numbers, and sum up to give 9261. Let's have a look at 32 cubed. I'll do it down here. 32 cubed. The cube of the first digit is 27. Now, this time the ratio is 3 to 2. And the easiest way to do that is to divide by 3 and multiply by 2. So 27 divided by 3 is 9. Multiplied by 2 is 18. Divide by 3 and multiply by 2 gives 6 times 2 is 12. And then 4 times 2 gives 8. Again, you'll see that 8 is the cube of the second digit 2. We double the middle two, giving 24 and 36. And then sum up. 8. We get 36, so 6 with 3 to carry. 54 add 3 is 57, which is 7 with 5 to carry. And 27 add 5 is 32. So it's 32,768. I'll look at one more example to show a more advanced aspect. And I'm going to, it's 39 cubed. I'm going to do this in two ways. Because if we just leave the 39 like this, the numbers get quite large. So you'll see 3 cubed is 27. So that's the first number. Now the proportion here is 1 to 3 in simplest terms. So we multiply this 27 by 3 to give 81. Multiply that by 3 gives 243. And multiply this by 3 to give 729. See, the numbers are quite large here. So let's carry on. Double 81 is 162. And double this is 486. And we have to take a bit of care when adding up. On the right we've got 9 with 72 to carry. Now to do this addition, I'm just going to add the units, the ones digits first. So get 11 and put the carry 1 here. Then we've got 48 add 24 is 72. Add 7 is 80. So we've got to carry 80 across to the left. Add up the ones digits to give 3. And add the remaining digits here to give 32 and carry that to the left, 32. And then we can add up for the rest, 59319. But there is an easier way to do this, and that is with by using a bar number. So I can call 39 40 bar 1. In other words, 40 minus 1. So I'm going to use this. The cube of 4 is 64. And this time the proportion is the ratio is 4 to minus 1. So I'm going to divide this by minus 4 to give minus 16, which is bar 1 bar 6. Divide that by 4 to give by minus 4 to give plus 4. And 4 divided by minus 4 is minus 1. Then we double the middle two, get 8, and bar 3, bar 2. And now we can add up. Here we get bar 1, get 12, which is 2, with a 1 to carry. We add up this and we get minus 47, because minus 48 add 1. So minus 47 is a bar 7 carry bar 4. Sum up this, we get 60. But we've got these winculum numbers, so you're going to have to devinculate. 60 take away 1 is 59. 7 from 10 is 3. And this is equivalent to 20 take away 1, which is 19. So we've arrived at the same answer, but the arithmetic is much easier. So what you can do now is have a little practice at 11 cubed, 41 cubed, and 52 cubed. You can stop the video and have a go at those. So 11 cubed will come out to be 1331. 41 cubed. I'll just go through this. 64, 16, 4, 1, 8, 32. We'll sum up 1, 12, 49. 68, 68921, and 52 cubed. The cube of 5 is 125. Divide by 5 multiplied by 2 for the ratio. 125 divided by 5 is 25, multiplied by 2 is 50. Divide by 5 multiplied by 2 is 20, and then 8 is the last. We double these two and sum up. We get 8, 0 with 6 to carry, 6 with 15 to carry, and 140,608. But now let's have a look at how this works. Okay, so I'm just going to imagine that our 2-digit number is AB. We're cubing it. And the first step was to set down the cube of the first digit. Now the ratio A to B means that we divide by A and multiply by B. So the ratio is equal to B divided by A. On multiplying A cubed by B over A, we get A squared B. And then multiplying by this by B over A, we get A times B squared. And then multiplying this by B over A, we have B cubed. And on doubling, we get 2A squared B and 2AB squared here. And then we can add up, and the result is A cubed 3A squared B, 3AB squared, and B cubed. And you should recognize this as really the expansion of A plus B cubed, the binomial expansion as shown here. And that's what it is based on. Well, now I'm going to look at binomial expansions using calculus. And this is a rather interesting relationship between differential and integral calculus and binomial expansions. Now I'm going to assume that you know how to do basic binomial expansions, and in fact I think what we'll do is look at this very example here, a plus b cubed. And the first step is to set down the first term to the given power here, which is a to the power of 3. Now what we're going to be doing is differentiating and integrating. Actually, we set down a to the power of 3, b to the power of 0. So it's the first term to this power, and then the second times the second term to the power of 0. Now, just to remind you about differentiating, if we have a term such as 2x to the power of 5, and we want to differentiate it, we multiply the power by the coefficient to give 10, and then reduce the power by 1. So that's the process of algebraic differentiation. And integration, let's suppose we have 3x to the power of 4, and we want to integrate it. It's the reverse process. So we increase the power by 1, so 3x to the power of 5, and then divide by the new power. These are two very simple algebraic processes. Right, now I'm going to apply that here, where we differentiate the a cubed with respect to a, and we integrate b to the power of 0 with respect to b. So differentiating differentiating a cubed gives 3a squared, and integrating b to the power of 0 gives b to the power of 1 divided by 1. And then all we do is just repeat the process. So we differentiate 3a squared to give 6a to the power of 1, and integrate b to the power of 1 over 1, which is b to the power of 2 over 2. And finally, we differentiate 6a to give 6, and integrate b squared over 2 to give b cubed over 2 times 3. And on simplifying, you will see that it gives a cubed plus 3a squared b plus 3ab squared plus b cubed. So let's have a look at another example, which is 2x plus 3 to the power of 4. So we set down the first term, 2x, and put it in brackets to the power of 4. And the last term, 3, we'll use a dot to indicate multiplication, 3 to the power of 0. Then differentiate the first term, give 4 times 2x to the power of 3. So I'm differentiating with respect to 2x, not to x. And integrate 3 to the power of 0 with respect to 3, giving 3 to the power of 1 over 1. And then continue. Differentiate, we get 3 times 4 times 2x to the power of 2, and then 3 to the power of 2 over 2. And then repeat, get 2 times 3 times 4 times 2x to the power of 1, and then integrate this last term, get 3 to the power of 3 over 2 times 3. And then finally, plus, differentiate the first term, we get 1 times 2 times 3 times 4 times 2x to the power of 0 times 3 to the power of 4 over 2 times 3 times 4. And then what we have to do is simplify all this. So the 3 to the power of 0 is 1, and 2x to the power of 4 is 16x to the power of 4. And here we'll get 8 times 4 is 32, times 3 is 96. So we get plus 96x cubed. Plus. We can simplify 4, 4 is 16, multiplied by 27, divided by 2 is 8 times 27 is 216, I believe. I hope I haven't made a mistake there. X squared plus, now I'm going to cancel through here, and then you get 27 times 8 again. It's another 216 x, and then at the end we've got a 1 here. The 2, 3 and the 4 cancel, and we're just left with 3 to the power of 4, which is 81. And there we have it. Now that might seem too much of an advantage from the ordinary formula, but it is very simple to remember. But it does have an advantage when it comes into when we use it for power series. And these power series, such as finding the expansion for let's see, 2 plus 3x to the power of minus 2, 2 plus 3x to the power of minus 2. Now this is going to be expanded as an infinite power series, and unconventionally we don't need to take a factor of 2 out here so that we have a 1. So that the normal Maclaurin expansion requires us to have a 1 as the first term, but using the calculus method we don't need to do that, as you will see. So I set down the first term, 2 to the power minus 2, and we're going to multiply that by 3x to the power of 0. And then we differentiate here. I'm going to put plus and deal with the minus signs later on. Got minus 2 times 2 to the power of minus 3, we're reducing the power by 1, times 3x to the power of 1, plus, differentiate again, minus 3 times minus 2 times 2 to the power of minus 4, times 3x to the power of 2 over 2, so we integrate that. And we can go on. And then all we need to do here is simplify. Here we've got a 1, and this is 1 over 4. Simplify this. First of all, pick up the deal with the signs, so that's a minus. And then we've got 2 over 2 cubed, which is 1 over 4, times 3, so it's 3/4. X. Deal with the signs here, we get plus. And what have we got here? We've got 3 times 3 times 3 is 27. And these two can cancel. It's 27 over 16. x squared, and we can continue for as far as we like, and this gives a power series expansion of 2 plus 3x to the power of minus 2. Another way of doing this, which I will show in a different video, is to set up a division, because 2 plus 3x to the power of minus 2 is the same as 1 over 4 plus 12x plus 9x squared. And the Vedic maths system has a really neat way of carrying out this division. And in the video on division, I'll show you how to do that. So we have looked at this method of doing a binomial expansion, and you should have a go at some yourself and try it out. It's really easy to remember. You don't need to remember this great long formula. You just do once you've set out the first terms, you just differentiate and integrate, differentiate and integrate. Now you did notice, however, I was doing things like integrating with respect to 3 and differentiating with respect to 2x, and this is it's a bit naughty really, but I call it the naughty calculus, because we're treating the two terms in the binomial as like algebraic entities which we can differentiate and integrate. And it's rather surprising that this formula that I came up with some years ago is not in the conventional textbooks, because it's so easy to remember. And it does give this very intimate link between calculus and binomial expansions. And binomial expansions are a very important part of mathematics. So good.